Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at algorithms. So algorithms are basically just lists of instructions that we perform in order to solve a problem or perhaps calculate something. So one such example is this algorithm here for calculating the greatest common divisor or highest common factor of two natural numbers m and n. Now this is written in what we call pseudocode. This just contains the instructions we would give to a computer, but we couldn't execute this algorithm by copying and pasting it into like Python or C++ because the grammar wouldn't be correct. But this is what we'd tell the computer to do. We would start off assuming that the greatest common divisor is 1. Now this step here says we're going to take each natural number successively. So we're going to try 2, then try 3, and so on. If the number we try is both a factor of m and also a factor of n, it overtakes the previous number as our highest common factor. So here we have a loop and it will end when we get up to the minimum of m or n, because of course the greatest common divisor of two numbers can't be larger than either of the numbers. Now here we've had to end the if and for loops. Of course, you don't have to do that in Python. In some languages like C++, you just use a brace. So that's why, for example, the grammar wouldn't be correct. Finally, down here, we return the greatest common divisor. Once we've done all that, we've checked all the numbers, it will just tell us what the greatest common divisor is. Now, this algorithm does work, but it would be inefficient. Now, we're checking every single natural number from 1 up to the minimum of these two. What if these were really large numbers, like many, many digits? This program would take a long time to run and to calculate. So that's why I say it's inefficient. Let's look at a more efficient algorithm for calculating the highest common factor. So here we will look at Euclid's algorithm, or the Euclidean algorithm. This is one of the first known algorithms in mathematics. I think it's about 3,000 years old. We're going to use it to calculate the greatest common divisor of 972 and 2076. Now we're going to do this by hand, so clearly we don't want to check every single natural number up to 972 to see if it's a factor of both. What we do is this: we take the larger number, so in this case 2076, and we write it as something times the smaller number, in this case 972, plus some remainder. So 972 goes into 2076 twice. So if you times these two together, you get 1944. The remainder left over is 132. So now we sort of shift these along. I want to write 972 as something times 132 plus a remainder. So 132 goes into 972 7 times. 7 times 132, 924. The remainder is 48. So we're going to perform that step again. We're going to write 132 as some number times 48. It's 2 times 48 is 96 plus 36. And then we have 48 equals 1 times 36 plus 12. We keep going until there's no remainder. 36 equals 3 times 12. This number here is the greatest common divisor. You can see I was able to do it in 5 steps. Much fewer steps than if I used the algorithm on the previous slide. So let's take a second to look at runtime. So runtime is how long it would take the computer to perform the algorithm and calculate what it was supposed to. And it's obviously affected by a number of things like the capacity of the computer. But we look at runtime as well in terms of ON. This is big O notation. It gives an indication about what happens as you change the input size. To illustrate this, we'll look up a word in a dictionary. So there are 2 ways, or 2 little algorithms that you could use. You could look at every page. If you find it, stop. Otherwise, go to the next page. Or you could open up to the middle of the book. If the word comes before that page, ignore the second half, otherwise ignore the first half, and keep repeating until you find the answer. So if you were looking up a word in a dictionary, you could check every single page until you get to the word, or you could successively halve the book to make your search quicker. Most people naturally would do something like this. So the first algorithm, very inefficient. It has what we call runtime complexity ON. This is linear. So if you have runtime complexity that's linear, it basically means as the input size doubles, so too does the amount of work that the computer needs to do. Now, this is not an exact number. Sometimes, for example, if you use this algorithm, it may be very quick. The word could be on the first page. We're sort of looking here about the worst case scenario. So we're thinking here, if you were to double the size of the dictionary, you'd have to do twice as much work. But let's look at what would happen here. It has running time complexity of order log n. Now, it doesn't really matter the base here, but the log function gets large very, very slowly. So what is happening here is if you were to double the size of the dictionary under this algorithm, you wouldn't double the amount of work. It would only be a fraction of that increase. And so it is with the two greatest common divisor algorithms I showed you previously. The first one, which was very inefficient, which involved checking every number up to and including m or n, it has linear running time complexity. So if you double the number, you expect to double the amount of work. So it's really inefficient like this one. On the other hand, the Euclidean algorithm, its running time complexity is log of a number. So it's similar to this one here. If you increase the numbers, you make them larger, you don't actually increase the work the computer has to do by anywhere near as much. And that's why the Euclidean algorithm is a far more efficient algorithm than is the first one. All right, let's take a look at another type of algorithm. So let's look at an example of a sorting algorithm. These are very important in computer science. Often you have to sort lists of numbers or words. We're going to sort this list of numbers here from smallest to largest. Now, this algorithm is called insertion sort, and the steps are here. So it says take the first number and append it to an empty list. So we start with nothing and we add a 5 into this list. So then we look at the second one. That's a 2, so we're going to put it to the left of 5 because it's smaller. Then we look at 4, so it's more than 2, less than 5. It's going to be to the right of 2 and to the left of 5, so we put that in here. Then we take 6, it's larger than 5, so we put it to the right, and of course 1 is smaller than 2, so it goes to the left. So our final list looks like this. Now this here, the insertion sort, is still an algorithm. It is a list of steps we follow. It was unambiguous and it helped us perform a task. But once again, it's a very inefficient algorithm. There's surely more efficient ways that we could sort a list. And of course there are much more efficient algorithms out there. But I wanted to show you that this is order n squared. So that means as you say double the number of items in the list, you expect that it's going to take the computer about 4 times as much work. So this is a very inefficient algorithm. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.